spatial resolution.
Okay, thank you.
Thank you very much for the questions. Thank you, Tom, for your talk.
Thank you.
And now to continue our discussion on PET and quantum entanglement, we have Ruth Newton from the University of York.
Good
morning.
Right, is that doing something good?
Yes,
Wonderful.
It's going perfect. We have full screen. Thank you.
Nice. Okay, yeah, so thank you for inviting me. And I'm basically continuing on from Dan's talk earlier about how we can use the quantum entanglement of these annihilation photons to enhance PET imaging. So I'm sorry, you must all be sick of PET by now. Positron emission tomography, and we use it to image metabolic processes in the body. So think finding cancerous tumors, monitoring brain activity kind of thing. Works by injecting a radio tracer, which is just some radioisotope attached to a sugar, injected into the bloodstream, travels around and gets absorbed into the tissues. When it gets there, this isotope will then decay, which produces our positron. Positron travels a couple of millimeters, hits a nearby electron in the body, and the two annihilate. And it's that annihilation that produces our two back-to-back photons. We can detect these two photons by placing the patient inside a big ring of detectors. When we get two coincident hits within the same time window, so think 10 nanoseconds or so, then we can draw a line between the two hits, and we know that somewhere along that line is where this decay must have taken place. When we get enough of these lines, you can see how we can start to reconstruct an image from this. Now, this is, of course, the absolute ideal scenario, and it's called a true event. So the photons exit the body, they interact with absolutely nothing, and they're instantly detected in our scanners. Now, of course, we live in the real world, so what can actually happen is that one or both of your photons scatters prior to detection. So this could be in the patient, on the table, in the air, even in the detectors. And now the line of response is going to be offset from where the decay actually took place. The third type of comet event is a random coincidence. So if we had a particularly high activity, it might be that two decays occur at almost exactly the same time. We could detect one photon from one decay, one from the other. If they come in the same coincidence window, we falsely assume that's a true event. And you can see again, the line of response is going to be offset. So these offset lines of response, they create noise and artifacts in our final images. To give you an idea, in a 3D scan, particularly around the torso where we're bigger, these can make up 30 to 50% of everything that we detect. So it's no small feature here. So the aim really is to be able to separate out our true events from our noisy, scattered and random events. And as Dan introduced earlier, we want to be able to do this using quantum entanglement. So as he said, there is only one state that can describe our two photons, and it's an entangled state of their polarizations. We can use the Compton scattering cross-section, which is dependent on polarization plane, to be able to analyze this. For this entangled wave function, we end up with this cos2 delta phi term come in. And that's just the delta phi is the difference between the two scattering planes of the photons. And for entangled photons, that has this nice big amplitude shown by the blue. So our theory here is that only our true quantum entangled good events can be described by this blue curve. Only they would still be entangled on arrival at our detectors. If we had a scattered event, well, then entanglement would be destroyed. So best case scenario would be this red curve, but we're likely to maybe see some rotation of the polarization plane when it scatters, so probably even less. If we had a random coincidence, well, we've no idea where those two photons came from. There's absolutely no reason their polarization should be correlated, so we'd expect a flat distribution. And it's this that we want to use. So as Dan showed, we have incorporated this into GN4, so we can now simulate this entangled effect. And we've also shown that we can measure it in the lab with our cadmium zinc telluride detectors. The next thing to do naturally then is see if we can actually use it. And we want to see if we can use it in PET. So I need a PET scanner. And for this, we simulated it in our quantum entangled GN4. My scanner is made of 4 rings of these cadmium zinc telluride crystals we used before. And the object we chose to image is a Nema mouse phantom. So a phantom is something designed to mimic the attenuation of a real patient, or mouse in this case. It's basically a little cylinder of plastic, and it's got 5 rods that run through the middle. So these rods contain a mixture of water and radioactive source. Think of them like the tumor in the patient. It's this that we're trying to image. So we set off our scan, we look for pairs of coincident photons, and when those photons scatter in the detectors, we make sure we record the angle between their 2 scattering planes. And that's what's shown in this image on the left. So this is just a histogram of delta phi's for all the coincident photons we detected. And you can see that nice big cos2 delta phi modulation there. On the right is just an image reconstruction of a cross-section through that phantom. So you can see the 5 bright circles where our sources are. This image was reconstructed only using lines of response, which had a delta phi around 0. So these are the lines of response we think are probably least likely to be entangled. So they're most likely to come from our scattered or our random events. If we do exactly the same image, but use a slightly higher section of delta phi, then we expect to include a higher fraction of true events. Does seem to get a little clearer. We can keep doing this for different delta phi sections all the way up to d phi of 90, where we expect to be including the highest proportion of true events. And I think that's a nice demonstration of how just by chopping on delta phi like this, we can show noticeable image improvement. And I should point out that though there are more events which scatter with a delta phi around 90, that's just how the cos works, all of these images were reconstructed using the same number of lines of response. The only thing varying between these is delta phi. We can also try and do something a little bit more complex. So if you look in the top left again, that is once more a cross-section through our phantom. But this time we're going to look at profiles through the bottom 2 capillaries along here. On the right, so this blue line is capillary 1 and capillary 2. The blue curve was reconstructed from an image made only using lines of response around 90. So it's basically a profile through the best case scenario from the previous slide. The green curve is the same profile through the 2, but only using lines of response around 0. So worst case scenario. We know that the delta phi distribution we detect, that is the sum of the delta phi distribution from our trues with a nice big amplitude and the delta phi distribution from our scattered. Because we know the amplitude we expect from both of these, it actually allows us to calculate a weighted distribution. So we can do a weighted subtraction of these 2 profiles and pull out a prediction for what scatter has done to this background, basically, which is shown by the red curve. So that's just a weighted subtraction of those 2. Because we're working in GN4, we actually know what happened as well. So even though I don't know what the scatter distribution looks like, I can turn back to GN4 and ask for only scattered events. And if I reconstruct using only scattered events and I take a profile through that, we get the blue curve. So the dashed line that you see here, that's just a polynomial fit to our red data. And it's really not doing a bad job there of approximating the scatter profile. So this is really quite a nice result. On the right, we did exactly the same thing. We can once more calculate a weighted subtraction of the 2 profiles and pull out the contribution we think trues have made to this image. And that's shown by the red curve there, which you can't really make out because it is directly underneath the real true profile that we can extract from simulation. So the really beautiful agreement between those 2 is a really promising result. We can do this slightly differently. Rather than trying to correct for scatter, I can simulate another PET scan, but we put in a really loud random background to it. And that's shown in the top left. Once more, I can do my 2 profiles through those bottom 2 capillaries, shown in the top right, and calculate a weighted subtraction of the 2 to pull out a prediction of what the randoms have done to this profile. And that's shown by the red curve. Again, we can compare this to the ground truth from GN4, so the real random profile, and that's shown in the blue, and the nice agreement between those 2. And then on the right, we do the same thing again. We can pull out a true profile of what we think trues have done to the image. And once more, it's in nice agreement with GN4. So in conclusion, as Dan has shown, we've incorporated quantum entanglement into GN4 and then verified it by comparing to some CZT PET demonstrator system. Now I've shown that we can also simulate some fairly complex phantoms using this quantum entangled GN4, and that purely by just chopping on this delta phi information, we can show noticeable image improvement. And then at the end, I showed a very kind of basic algorithm to pull out the contribution of scatter and randoms to our images. So thank you very much for listening, and thanks to all these folks here.
Oh, thank you, Ruth, for an amazing talk. We've had some very good comments for you in the chat that you can read. Are there any questions for Ruth? Tom has his hand up.
Hi Ruth, it's really interesting to see that. I wonder what are going to be the real difficulties to do a practical implementation of this? I mean, I see that you use CZT just because the scattering cross-section is much, much higher, but you presumably rely on both photons scattering and then absorbing, so you get the angle. And so the efficiency is going to be quite low compared to photoelectric absorptions.
Yeah, so with CZT, we do get more of the scattered effect. We're currently in the process of simulating the same thing in LISO to see if we can apply this to much more commonly used PET detectors in clinical setups. But I guess the big point here is that in order to chop on this data, we have to limit to a very small fraction of the available data. So it's not a particularly, that would not be the approach we'd want to go down, because throwing out data in PET is never going to be a good idea. So the idea would be purely to use this as an addition to the data we already have. We want to be able to pull out these backgrounds, things like this, perhaps incorporate this delta phi modulation in MLEM or one of the more advanced algorithms to bias the way we reconstruct our images.
Yeah, no, I think that's very sensible. And the other problem that you'd have eventually would be a clinical implementation of this, because nobody will want to change their
of course not. Yeah.
That's fine. Thank you.
Thanks.
Thank you for the question. We have another question from Jack Anderson. Jack, if you'd like to speak up.
Hi. Sorry. I was just wondering how this kind of technique you feel would compare to kind of more conventional, I want to say, methods for dealing with the problem. So like selecting on the energy to get rid of scattered events, and selecting and maybe doing kind of a time random background subtraction to subtract the background as compared to your technique. I mean, it's incredibly neat and it's amazing. I'm just not sure, how does it compare to the kind of the standard way of doing things? Yeah,
so it semi-relies on a slightly higher energy resolution, which if you had a higher energy resolution in a normal PET detector, you would also have better cuts on these scattered and random events. But I think, again, that the push is that we'd want to use this in addition to everything else, because we can use it without affecting the rest of our data. It is just extra information that's currently not being looked at.
Okay, I mean, yeah, it's obviously, it's very convincing. It's just, I was just trying to work out how it compared. So if you get it for free as well, you might as well use it.
You might as well, yeah.
Yeah, and maybe I'd just, I mean, the PET simulation that Ruth presented doesn't essentially have an energy resolution. We essentially don't imply an energy window. Mm. So that's what's achievable if you have just hits.
So you could do it with a truly terrible energy resolution scintillator if you wanted to.
Yeah.
Interesting. Thanks.
Okay, thank you. Simon has a few points that he would like to discuss before going to his next meeting. Simon?
I think there's only really time to say it was a fantastic session, and thank you so much to all speakers, and particularly this last one. I think it was very much how I thought it would be, but beautifully executed. So I really hope I can find something more in the literature, and I was just going to ask if you actually did a performance study, you know, for us like a statistical analysis, because obviously you don't have perfect separation with this entanglement. It's got a certain efficiency in selecting out the non-scattered events. And is there any kind of performance study to look at, given that efficiency and the price that you maybe have to pay in losing events to get the non-scattered ones? That's my question. Thank you.
That is basically next on the to-do list, I believe, is trying to find a compromise between these two factors and a happy place in the middle.
Yeah,
Okay.
I'll just maybe add, Ruth, if you don't. I mean,
Of course, please.
The simulations that Ruth did were for a typical event sample that you would get in a PET scan. So the accuracy with which those scatter backgrounds were determined is what you would achieve in a real scan. And that was for a mouse where the scatter fraction was below 1%. So obviously, if you're thinking about whole body PET, you're going to get a lot more statistical accuracy in what you extract. And I mean, the jitter in what was extracted wasn't statistics. The statistics in the bins would give a much smaller error. They're imaging artifacts because we used a very simple filtered back projection. Yeah, so these up and down, that's you know, due to gaps in the acceptance and other things that feed through into the filtered back projection. Whereas the statistical accuracy is much better. So I mean, this averaging is not a statistical averaging, it's an averaging over the imaging artifacts. And it pulls out both the shape and the magnitude of the scatter contribution. So this isn't normalized, this is absolute. So I guess in terms of when you incorporate this into an MLEM, where the shapes of these scatter things are approximated with Gaussians and you have to iterate, you know, this would be a starting point for MLEM, for example, would be one way. But intrinsically, just from the data, you can essentially subtract the scatter contribution.
Okay. Thank you, folks.
Was there any other comments or questions for Ruth? No? Okay, well, hopefully we can keep the very interesting discussions that we started this morning going. We can keep them going after the taste. Dave, did you have something to add? David? No? Oh. Yes? Okay. So before we go to lunch, I just want to thank everybody, of course, for the amazing discussions and presentations. Many people were very interested, so we all learned many things this morning. I want to remind you that at 3:30 there will be the Student Awards, so you do not want to miss that. And in order to catch up on the schedule, we will have a 30-minute break for lunch. So we will start again at 1:30. So enjoy your break and your lunch, and we will see you soon.